Thank you very much. I was sat in the coffee shop this morning and I was looking at some people delivering their children to university here. And it occurred to me that it's 22 years since that happened to me. When I delivered to Martin my education as my PhD for a geologist. Martin's had lots and lots of students, and I think that I'm probably one of the more eclectic ones. I started out as a trace fossil worker, and I've diversified into all kinds of different things, all the way to geochemistry and reservoir modeling, sequence stratigraphy. But always I keep coming back to some of the problems that Martin and I spent a long time discussing during my PhD and in the years following. Martin's very much been a mentor to me for the last 22 years. One of the things that we always pondered as I was doing my PhD with the Precambrian and the Cambrian was why there were so many blooming cracks in the mudstones. Wherever you go in the Cambrian and the Precambrian, and even up into the Ordovician, there are cracks everywhere. Conventionally, we call these syneresis cracks. And that was something that Martin and I discussed at many, many junctures and never really got to a very satisfactory answer. We knew that they were there when you get the first trace fossils, when you get the first blobs, the things in the later parts of the Ediacaran. And it was only really by accident that I came around back to this. I had a PhD student who was going to start doing some work on shale gas deposits. We have some deposits in Newfoundland that are shales. And some of the intervals, they're Ordovician in age, are completely unbiturbated. They seem to be shore face, but they're completely unbiturbated muds. And the question I set him, just as a training exercise, really was, why on earth would they not be biturbated? If you go to any modern shore face, and you look in the lower shore face, there's animals everywhere. They're disturbing everything. And so what we did was we worked through this and used tools that were, I guess, I'd been exposed to through Martin, so the geochemistry and the petrography, and really got to grips with actually the detailed geochemistry and petrography of some of the mudstone units in the Ordovician. But the rules I think that we've established will actually go back into the Precambrian. So the first thing that we that we addressed was really, are the mudstones that we're seeing in the Precambrian and Cambrian that have all of these fossils in, are they actually low energy deposits? And actually they're not, they're high energy deposits. So the question remains then, so is it salinity that people have often said is the cause of syneresis cracks? Or is it maybe oxygen stress or something else? So we started trying to test some of those problems. And we also wanted to have a look at what the bioturbation, when you do actually see it in some of these beds, what that actually does to the geochemistry of the beds. And I might not get to that, so I warn you now. So we looked at the beach formation. This is literally 20 minutes drive from the St. John's campus. Lots and lots of strata. There's about 1 kilometre of strata. Most of it is actually mud. And people have suggested that the unbiturbated black shales within that are caused by salinity stress and that they were shallow marine. And they interpreted lots of the cracks that are in there as desiccation cracks. But they're not desiccation cracks. So I set my student Dario Harazim on this. It's basically, as I said, a training exercise. And so we went to the outcrop. We found one of these intervals that was weirdly unbiturbated. And he collected hand samples like this, and he polished them up. And he made thin sections, and he did total organic carbon, delta carbon 13, bulk element analyses. And he started to come up with some really interesting data. He had a history from working on the Jurassic. He was an isotope stratigrapher. And at a couple of intervals through the succession, there were some anomalous data points that he wanted to throw out. And my experience with Martin is that you don't throw out data points. You look at them really, really carefully before you do anything like that. One of the things that we found was that these anomalous data points actually coincided with very black shales with syneresis cracks over and over again. So these are the outcrops. So these are the bioturbated layers that you'll see in here. And you'll notice that between the sandstone layers, there's really dark mudstones in here. And those were the ones that we were really focused upon. They break out of the cliffs nice and easily. The cliffs are weathering all the time, not doing any real damage to the outcrops at all. So one of the things that the shale gas people in particular have been looking at in recent years is actually how mudstones are actually made up. When we see mudstones in the field, certainly as undergraduates, we see, oh, mudstone, just put a little line somewhere to the left of your log column and walk on. But actually, if you make thin sections of these layers, they're actually really, really complicated. I sound like Joe McQuaker now. I don't want to do that, but I can't help it. So you do see within what would appear to be a single black shale event, you do see lots and lots of little events. And in often cases, there are erosional surfaces. And some of the erosional surfaces are capped by mudstones, and they're actually eroding down into sandstone. So obviously the currents that were transporting and depositing the mud were capable of eroding coarse sand. Yeah? So these are high energy environments, not low energy environments at all. Sometimes we do get amalgamation of beds, so you see surfaces going through here, where you get slightly coarser lags at the base cutting into each other. So it just looks like normal hummocky cross stratification that you would see in a lower shore face, except much more fine-grained. Sometimes you do see burrows within the mudstones. Often they're associated with sandier intervals, which are probably more stable, less muddy intervals. This is Diplocaterian in cross-section here. But more normally you see unbioturbated muds with occasional sand-filled burrows, which are probably attributed to horizons that have been subsequently eroded. So they're not actually the animals that were bioturbating the muds themselves. It's something that's come in later. We always see these as being sharp-margined, which suggests to us that the mud was firm. And we have some evidence elsewhere that suggests when the muds were deposited, they were actually rather soupy. So we think these are really rather late burrows. So this is a nice example in here, and you can see that there's some evidence of current ripples and wave ripples, very nice pronounced erosion, and it's picking up some of the burrows. So the erosion's actually picking out the burrow in here. So we see evidence of combined flow ripples, starved ripples, so currents that were transporting some sand, but there wasn't enough to actually produce whole beds of sand. You just get little trains of ripples that follow each other around. And if there was any bioturbated mixed layer on the surface, as you see in almost all lower shore faces, it usually gets eroded away. So basically, as we went through this, we found that basically the mudstones are high energy. This is something that we've got published now and is about to be. So we're just doing some corrections ready for publication. But understanding that the muds are high energy opens up some doors to us. We need to actually think carefully about what's actually happening on these surfaces. And we think that the major controls on how the mud's actually preserved into the rock record is a combination of the seafloor processes and the energy and the time that the seafloor was exposed. So one of the things that we do have a lot of evidence for is microbial mats. And the more time you leave a stable surface on the seafloor, or the more times you erode down to the same surface, the more complex and more robust those mats are going to get. And that's really key. So the typical data that we have in here, this is the main succession that we were focused on here. The TOCs are in a normal sort of range for delta carbon 13 organic. And the total organic carbons were mostly in the range of 0 to 1.4, so really, really relatively low. Oops. And just to point out that the syneresis cracks occur at very specific horizons through this, and if you could track that across, they would come out as being rather negative and with high TOC. So when we see these surfaces, oftentimes we see them in core and we're looking at the vertical surface. But obviously we have the benefit in outcrop that we can actually crack the surfaces apart and we look at the bedding planes. And when we did that with the surfaces that had the that had the syneresis cracks on, we found these wrinkled textures that people have recently been started calling microbially influenced sedimentary structures, or MISS. The syneresis cracks themselves, you see they're not forming the nice polygons that you would expect with desiccation cracks, are exclusively within mudstones that are stratified, they're unbioturbated, and they're capped on their upper surface by these wrinkled surfaces. Sometimes there are scratch marks, probably of trilobites. They produce something called monomorphicness. And it's this facies M1 in here. And so you can see that there's a range of total organic carbon from 0 right up to 3.4. And it depends where in the bed exactly you sample. So down at the bottoms of the beds, the TOC is very low, but right up at the surface, if you sample just the surface, it gets up to 3.4%, which is actually really very high. That's nearly economic. Oops. And so this is what they look like in cross-section. And through my career, when I left Martin, I had to work in the oil industry just to make ends meet, really. I enjoyed it a lot, but I did come across a lot of syneresis cracks in the process. And they're always these wrinkly things. You know, I've cracked them apart on core. You're not supposed to do that, but I have done. They come apart on those surfaces, and you can see that they're syneresis cracks. They pinch and swell, but they're always wrinkly like this. And I never really thought it through. They're always wrinkly. But of course, they're wrinkly because they've been compressed. So the muds that they were deposited in, that they're formed in, were originally much, much thicker. So if you try to uncompress that, almost stigmatic folds, you end up with a bed that's like 5 times thicker than it was. So something has been lost from that bed, and basically the pore waters. So when it was deposited, or when these beds were deposited that have the syneresis cracks, they were really, really soupy. Something managed to seal the surfaces in, which we suspect was probably the microbial mats, and we have evidence for that from thin sections. So this is all kerogen from this topmost surface. Often it's very, very dark in here. If you sample through the bed, you find that the total organic carbon increases up towards the top, decreases again into the sandstone. And you get quite a range of delta carbon 13 from -24 to -28. This is within a single, 2 centimeter thick bed at the most. So from looking at these things over and over again and trying to figure out what happened in which order, we actually managed to find out that there's a consistent pattern to the deposition of the beds that actually have the syneresis cracks. So initially they're deposited as what are called fluid mud deposits. So these are really soupy muds. They're high energy muds, often in places such as, so a modern analog will be something like the Amazon coast, really, really muddy coastline. What then happens is that there's a microbial mat that grows on the surface. So in order to do that, you need to have probably high nutrient supplies, and also probably a little bit of time as well. But the interesting thing is that you don't see those surfaces perforated by trace fossils very commonly. You see things like trilobite scratch marks on the surface that we call monomer thickness, but you don't see things actually perforating right through and into the soupy layer underneath. And then something mysterious happens. So we don't have a solution for this. We're pretty sure it's not anything to do with salinity, but the soupy mud starts to aggregate. And in doing so, it's sealed in by an upper surface, and so it leaves cracks behind. So as the clay grains are coming together, they're forming agglomerations, and in between them they leave these cracks. What then happens is that this mud has these cracks in. It gets buried by subsequent deposits, and eventually, and you can tell this because of the source of the sand, the sand's very distinctive and it falls down into the cracks, so they were open structures. And that can only happen, we think, once the mat is compromised. So once the mat has been buried, it starts to degrade, and the sand falls down into these open holes. Subsequently, with subsequent burial, you get the compaction of this mud, so you get progressive dewatering. These things become progressively more folded, and you end up with the classic syneresis morphology. Now, this is really important because people have been suggesting that syneresis cracks are formed by rapid salinity fluctuations. So there's various groups of ichnologists, trace fossil workers, who have been using that as a first-order interpretation tool to say that we're in a saline stressed environment. And we see no need for that in this model. The other thing that's been suggested is that they're actually due to seismites. So it's seismic shaking that produces these cracks. We don't find they have any orientation, any consistent orientation. And we have no reason to suggest that. And this model seems to stand alone without the need to invoke anything like earthquakes. So that was kind of fun that I've come from being a trace fossil worker, I've gone into the petroleum industry, I've seen all these cracks, I've pondered about them, and then come back all the way back to the Ordovician, seen that they're so similar to the things that we saw in the Precambrian and the Cambrian, and we've actually we've actually been able to use some of the tools that Martin sort of equipped me with when I was here at Oxford to actually produce a working model that actually means that we'd interpret some rocks in a really rather different way. This is really quite important for the hydrocarbon industry. I seem to be doing okay for time.
You're into your next 5 minutes.
Okay, good. I will start winding up. I'll very quickly show you some of the other work that we've been doing on these same rocks. We've been looking at shale gas reservoirs. And one of the things that we wanted to understand was actually what trace fossils, which is my original background, what it actually does to the sediment geochemistry. I'm going to just basically give you a little taster of the data here. So we look at some really large burrows. We call these ficosiphon-like burrows. These are about 0.5 centimetre across, which means that we can actually accurately sample different parts of the burrow. So what we did was we analysed the host matrix. The dark bit in there is a fecal string in the middle of the burrow, and what we call the halo is basically clean sediment from around where the animal was. And what we found really interestingly was that there's differences in total organic carbon, the weight percentage. More of it was concentrated in the core, but also that the core and the halo had different delta carbon 13s to the host sediment. So the animal in processing the sediment is actually fractionating delta carbon 13 in the sediment itself. And this goes right back to the first paper that Martin and I actually published together, which was suggesting that biotubation was one of the causes for some of the changes in the carbon isotope curve around the Precambrian Cambrian boundary. So I'll skip that. The other thing that we did, and this is very much down to Dario. Dario is very much a geochemist, and he loves grinding up things and putting them into machines and getting data back out again. One of the things that was really interesting that we found was that in some cases, the elemental proportions between the core and the halo were really, really very different. Things like vanadium, chromium, magnesium, cobalt, but also strontium and barium seem to be relatively fractionated in the material that's been through the guts of the animal relative to the bits that haven't. So it seems that the organisms are breaking down the minerals and they're actually redistributing, remobilizing elements in a way that wouldn't be possible in life before biotubation. So in the Precambrian, this isn't possible. This comes back to some work, experimental work that I did with modern organisms, which demonstrated that you can actually produce orthogenic minerals in the guts of organisms. And we demonstrated this again for the first time in the rock record with these rocks, in that the original rock was low in things like smectites, so swelling clays, but actually the fecal material, the material in the core, is actually rich in these swelling clays. Which is kind of interesting. It takes us back to a paper, a provocative paper in 2006 by Kennedy et al. Mary Rose is involved in that as well, which noticed this big spike, or interpreted this big spike in the marine strontium isotope record as being due to the evolution of a primitive land biota. But if you look at the timing of that, that's right down at the Precambrian-Cambrian boundary where we first start getting biotubation. And I would suggest to you that there's very significant possibility that this remobilization of strontium may well be due to weathering by macroorganisms, by biotubators. The reasons for these fractionations of things like vanadium, chromium, cobalt is probably something to do with microbes. Those are all really important microbial micronutrients. And there's still a story to be opened up there. And let's get to that, because I'm going to get told off. So this has really been a great privilege for me. Martin has been very much, as I said, a mentor for me for a lot of years. And I was thinking about Martin and his impact, and basically it goes down through the generations. So I was Martin's first sort of Precambrian Cambrian student that's kind of stayed in the field. And between us, we've co-supervised students, and basically all of the information, all the problems that we discussed, they go round and around, and eventually they will get solved. So thank you.